In the last lecture, we had looked at some of the limitations of the unit hydrograph theory, and we have also looked at ways to go about it, how to solve these problems. For example, if the catchment area is very large, we cannot apply the UH theory, and then we can subdivide it into smaller areas, apply the unit hydrograph theory, and route the flow through the channel. Or if the rainfall is non-uniform, we can derive an instantaneous unit hydrograph, IUH, and apply that to get the direct runoff because of any non-uniform distribution of the rainfall. In the third problem which we faced, there was a lack of data. So if the stream is not gauged at a particular point, or if storm events of that particular duration are not available, then we cannot develop the unit hydrograph for that catchment. For that purpose, we already described methods known as synthetic unit hydrographs, which correlate some of the hydrograph properties to some of the basin properties. And since the basin properties can be easily obtained, we can obtain the synthetic unit hydrograph for that area using some relationships which are mostly empirical based on observations of existing gauged catchments. So let's look at a catchment where there is no gauging station. So the point A is not gauged, and therefore we don't have any data about the runoff due to corresponding storm event. In absence of this data, we can try to correlate some of the features of the hydrograph So let's say that the duration of the rainfall is Tr, and we can define a time to peak from the centroid of the rainfall as Tp. Based on a lot of data about existing gauged catchments in the eastern United States, Snyder in 1938 came up with some relationships which relate the lag Tp, which is the time from the centroid of the rainfall to the peak, with catchment properties. So some basin properties can be used to obtain Tp. What Snyder did was the basin properties he described in terms of two main variables: length of the basin this is from the point A, the outlet point, to the water divide along the stream. So this length is not a straight line distance between 2 points, it's along the stream, curving length L. The other parameter which he chose was based on the centroid of the area. So if this point C is the centroid of the catchment area, then the point directly opposite the centroid on the stream, let's call this point C prime. The distance of C prime from A, again along the stream, was termed as length to the centroid, and we would write it as LC. So using these two parameters, L denotes the size of the basin because larger L value means a larger size of basin, and LC represents the shape of the basin. So if the basin is wider near the point A, LC would be smaller. If the basin is wider away from point A, then LC would be larger. And what Snyder found, that the time to peak from the center of the rainfall was related to LLC to the power 0.3. So for any catchment, if we know L and LC, which we can measure from the topographic map of the area, then we can find out for a hydrograph of duration TR, unit hydrograph of duration TR, which was related with the time to peak, as Tp over 5.5. So this Snyder called standard duration of rainfall, TR. And for this TR, the time to peak will be given by this equation. Now, in general, we may not want to derive a unit hydrograph of duration TR, and we may have the value of CT typically is obtained from a gauged catchment, which is similar to the catchment under consideration. So CT is obtained from nearby gauged catchment or gauged area. So in order to derive the synthetic unit hydrograph, we should have an area which is similar to the area under consideration, maybe a nearby basin where the properties are similar to the area under consideration, and for that area we should have a gauging station from which we can derive a unit hydrograph for that particular area. So let's look at a big basin, and let's say that we have one stream here, another stream here. We know the catchment areas of these streams at some points. Let's call these points A and B, and suppose there is a gauging station at point B. So due to a rainfall event in the area B, we can measure the runoff at point B, but at A we don't have a gauging station. So our aim is to derive the UH at A, and I will call it synthetic unit hydrograph, SUH. And this SUH may have a duration which is not equal to the standard duration TR. It may have some other duration. Let's call it T capital R, the required duration. So this capital R stands for required duration. Now the data available at B, again the rainfall event for this catchment area may not be of standard duration TR. So let's say that at B we denote the properties by variables which have a star. So the area of catchment B let's call it A star. Also, let's say that we have a unit hydrograph derived for this area. Since this is a gauged catchment area, we can derive the unit hydrograph for this area based on storms occurring in that area. And suppose we have derived the UH for a rainfall duration T star, and the time to peak for this UH is TP star. Now this TR star is the duration of rainfall for this unit hydrograph, which has a time to peak of TP star. Now based on these data, what we now want is to obtain the coefficient CT. What Snyder said that if there is any other duration, let's say TR star, which is not equal to TR, the standard duration, then the time to peak will also have to be shifted. So if for a standard duration there is some time to peak, and if there is another rainfall which is not of a standard duration, let's say this is longer than a standard duration, then the peak will shift to the right, and the distance to peak, Tp star. So if this is TR and TP, TP star will not be same as TP, and there is a relationship which is proposed by Snyder that TP star should be taken as TP plus TR star minus TR over 4. So this accounts for the difference in duration of the rainfall, the standard duration TR, and the actually occurring on the catchment area of B, TR star. So this helps us in obtaining the lag for the catchment area B. Now using these values, we can derive the coefficient CT for the area B. So what we do is we have this equation, TP star and we also have the standard equation which says that Tp is equal to 5.5 TR as proposed by Snyder. So using these equations, we can correlate the standard time to peak with the observed values of time to peak and rainfall duration, as Tp equal to 22 by 21 Tp star, which is a rather straightforward operation by just substituting this value here and solving the resulting equation. So using this information, Tp star and TR star, these are known because the catchment is gauged, and therefore we have unit hydrograph for duration TR star, and we also have the time to peak in terms of Tp star. So we can find out Tp, and then since we know the relation of Snyder, Tp is equal to Ct, and since this is on the catchment area B, I will put a star to the power 0.3. So using this relationship, we can obtain Ct, because once Tp is known from here, L star and Lc star from the basin, we already know this information because we have the data available for the gauged basin. Therefore, we can get Ct from here. So using this Ct, then we can obtain we can assume that this same Ct for B, this is Ct value for catchment B. But since we have assumed that both the catchments A and B are similar, we can say that the same value of Ct can be used for A also. So may be used for A. So that takes care of one of the coefficients, Ct. Now to find out the peak discharge, Snyder found another relationship, and he says that Qp will be given by some other constant Cp (2.78 A over Tp). Now this 2.78 factor comes by conversion of units of kilometer square and hours to get Qp in meter cube per second. So we take Tp in hours, A in kilometer square, Qp in meter cube per second, and this Cp again can be obtained from the data on the gauged catchment. So let's we know the value of QP star, we have the value of A star, and we also have the value of TP. So we can write CP and since everything else is known, we can obtain CP for B and assume that the same CP holds good at A also, and same as CP for A. Now this coefficient CP can also be written as, if we look at discharge, the peak discharge, due to a rainfall of duration TR, which just says that intensity should be 1 over TR because we are talking about unit hydrograph, and AP is the area which is contributing to the peak flow. Contributing to peak flow. If we want to write this in terms of Snyder's equation, which is QP equal to CP what we get is the value of CP as TP by TR into AP by A. TP by TR as per Snyder is equal to 5.5. AP by A will generally vary from catchment to catchment, and therefore the value of CP also varies depending on the value of AP over A, and it has been found to vary from about 0.4 to 0.8. So once we have the value of CP and CT, so we have obtained these values from B, and now we can use these values at A to derive a unit hydrograph for any desired duration TR. So at A we want to derive a UH for duration TR, capital R. So now we have to see how to go about deriving the unit hydrograph at A for a duration TR. If this TR is equal to the standard duration TR, then we don't have to do anything. But if it is not, then again we have to use the Snyder's proposal, and what we do is write TPR where this term is nothing but TP, and then we can write QP for the required duration TR as TPR. So this will give us the time to peak for the required unit hydrograph and the discharge at peak QP for can draw the unit hydrograph, but it will not be very accurate. What we have is only 2 points. This is QP, TR, and TPR. So we have 1 point here. Here we know it will start at 0, 0. The other information which we have is that the area under the curve should be equal to 1 centimeter of depth over the catchment area. So we may have a shape like this, or like this. So there are various other options also which all will have the same area. Therefore, some other points need to be given. One of the parameters which is normally given is the time base TB. This is the time base of the UH, and there are again equations provided for this time base in order to help us sketch the unit hydrograph. There are some other parameters, for example, the width of the unit hydrograph at some location can be given. In this case, suppose QP is the peak flow, we can find out what will be the width of the unit hydrograph at 50% of QP and call this W50. Similarly, we can also provide some equation for W75, which is at 75% of QP. So once we know these 4 or 5 different parameters, it would be much easier for us to sketch the unit hydrograph. So let's first look at this TB, the time base. What we do is we assume that the unit hydrograph can be approximated by a triangle. Which has a peak flow of QP and a time base of TB. Once we assume it to be a triangle, it's very easy to find out the area under the curve, which, knowing that Q is in meter cube per second and T is in hours, can be written as, the volume can be written as half QP TB. Now we have to take care of the units. So this QP is in meter cube per second and TB is in hours. So we have to multiply it by 3600 to get the volume in meter cube. Now this should be equal to 1 centimeter of depth over the entire catchment area. So this should be equal to area of the catchment into 1. the base is known. At 50% and 75%, we also know what is the width of the unit hydrograph. There are some suggestions as to how much of this width should be before the peak and how much after the peak. For example, some researchers have suggested 1/3 before peak and 2/3 after. So if this is the peak line, W50 can be put 1/3 here and 2/3 here. Some of the other researchers have suggested 2/5 and 3/5. So in a ratio of 2:3, some have suggested 1:2, some have suggested 2:3. So once we know that, then we have these additional points. 2/3 here, 1/3 here. So we have 1 point here, 1 point here, another point here, another point here, the base here. So now we have 1, 2, 3, 4, 5, 6, 7 points which we can join by a smooth curve and obtain the synthetic unit hydrograph. The check will be that the area under this curve should be equal to 1 centimeter of rainfall, and if it is not, then we will have to adjust some coordinate, maybe this dB we will have to shift this side or this side. So that little bit of adjustment has to be made in order to maintain the area under the curve equal to 1 centimeter of depth. So in this way, for any catchment which is not gauged, but a nearby catchment has a gauging station and which is similar to the basin under consideration, we can develop a hydrograph have been proposed. For example, if we take this equation, the CT parameter depends on the slope of the basin. So some of the investigators have put the slope of the basin also inside this variable, and then they have suggested using some formula which involves the variable LC over square root of S and to the power n and some factor CT prime. So these kind of suggestions have been there in the literature available to us, but we will not discuss those advanced techniques right now. This description of synthetic unit hydrograph should be sufficient for this purpose. Now, synthetic unit hydrograph or instantaneous unit hydrograph or a regular unit hydrograph, these all give us how the discharge varies with time. Based on these UH, we can derive the DRH. For example, if we know the intensity of rain is 1.5, the depth of rain is 1.5 centimeters, we can derive a DRH which will have everywhere ordinates equal to 1.5 times the UH ordinate. And once we get the DRH, we can add the base flow and get the total runoff hydrograph, which would look like this. Our aim of developing this total runoff hydrograph is to be able to answer questions like what is the maximum flow in the stream, what is the minimum flow in the stream, what will be the total amount of water which passes the stream for a fixed period of time, or there could be a lot of other questions like one question which typically people ask is what is the reliability of a certain discharge. For example, let's say 85% of the time, we say what is the discharge which we can assure will be available to us 85% of the time. So to answer all these questions, we would look at alternative ways of presenting the same information. So let's choose a time period. It may be 2 or 3 days, it may be a week, it may be a month. But let's say that the hydrograph during that time period is given by this total runoff hydrograph. Now, if there are some questions which are very easy to answer. For example, if somebody asks what is the minimum flow in the stream, we can say that this is the minimum flow. Then if you are designing for a flood control structure, you may have to answer a question, what is the maximum flow in the stream? That's also very easy to answer, Qmax. Now somebody might ask, what is the average flow over this time period? Let's call it T naught. So over this time period of T naught, what is the average flow in the stream? Or what is the total volume of water which has passed the stream at that location A in this time T naught? So for this purpose, there is a curve which we can generate from this hydrograph, which is known as the mass curve. And mass curve shows the volume of water, cumulative volume of water passing through that point in a given time. So we have T, and let's say we are concerned about time period from 0 to T naught only. So if you look at the accumulated volume, let's say in meter cube, time may be in hours, it may be in days or months, but let's for simplicity use a single storm hydrograph and see how we can develop these curves. So at time T equal to 0, the cumulative volume will be 0, and then as water starts coming in the river, the cumulative volume will be increasing. It will be increasing at a fast rate till the peak, and then the rate of increase will become slower as the discharge decreases. So we get a curve which is concave, then convex, then again it may become concave here, which tells us what is the average rate of flow by taking the slope of this line. So the slope of this line, this will give us total volume coming in time T0, So that also we will look at by a curve which is known as a flow duration curve. So let's see that from a given hydrograph, how can we obtain these quantities which are important for a water source engineer to know. So we have a minimum flow, Q min, maximum flow, Q max, and let's say we are analyzing this period 0 to T0, and we want to say what is Q50, means what is the flow which can be guaranteed at least 50% of the time. So this is flow which is, and we use the term equaled or exceeded. So at least this amount of flow Q50 would be available to us 50% of the time. So in order to find out this Q50, what we will do is we will take a line which is of width T0 by 2, 50%, and then we will have to shift this line up and down till this line fits exactly between the two curves, and this will give us Q50. Similarly, if you want to find out Q, then we must see what is the flow which is equaled or exceeded 85% of the time. So that means only 15% of the time the flow would be below that. So if we, let's draw this line here again. So this will be 0.85 T0, and again we fit that line which will be 0.85 T0. So this flow would be equaled or exceeded 85% of the time. So this is an important parameter. Sometimes when we are creating a facility for power generation, typically we take this 85% dependable discharge as our design discharge. So that means at least 85% of the time that much flow will be available to us. To answer these questions, we use what is known as a flow duration curve. Which plots this percent against Q. And this percent of time, when we write here, this is percent of time equaled or exceeded, and the curve would look like this. So there is some minimum flow which will be equaled or exceeded 100% of the time, Q min. There will be some maximum flow which will not be exceeded, so it will have a 0 probability of, or 0% of the time equaled or exceeded. And then from this curve we can answer all the questions like what is 50%, Q50, what is Q85, and so on. Now the flow duration curve and the mass curve, they are both very critical in water sources or let's say power generation design. We would first look at the mass curve to find out how much storage we would require in order to satisfy a given demand. So if we draw the mass curve, which as we have seen would look like this, during periods of high discharge, the slope will be larger. Then as the discharge reduces, the slope becomes flatter, and then if another storm comes, it will go up. Now we are discussing this on a very short time basis, maybe a few weeks or a few days, but generally this analysis is done for the annual flows. But to understand the concept, let's look at this curve first, which let's say is in response to the storm with the DR rate, with the runoff given by this. So this runoff will produce this mass curve where V is the cumulative volume. As we have seen, if this is the time t0, there is an average flow which can be thought to occur during this time t0. And we cannot supply this average flow, as we have discussed, because some of the time the flow in the river is not sufficient and it will not be able to meet the demand. If we want to meet this demand, suppose at point A, we can create some facility for storing water. Typically it is a dam built on the river to store water, but we can assume that there is some structure here which stores water. Now during periods of low flows, when the flow is less than the demand, we can get water from the storage to supply the demand or to supply the requirement which exists, suppose at this continuous rate. Of course, we cannot supply water more than this rate. Our Q supply, this is the maximum rate at which we can supply water, because this is the total amount of water available to us. V is the total amount of water available to us in time t0. We cannot supply more than this water. So this is our maximum rate of supply. Less than that, of course, we can always supply. So we can always supply anything at a smaller slope, but more than that we will not unless we take water from somewhere else. So let's say that we want to supply this maximum rate by creating some storage facility here. The question which is to be answered is, what should be the capacity of that storage structure? So from this figure we can see, if we draw the mass curve again, like this. So the idea is that during period of low flows, we will take water from the storage, and during period of high flows, we will divert the additional water from the stream to the storage. So if you look at this figure of the runoff, during this time our supply is less than the demand, and therefore we must take water from the storage. During this period, water will be going from the stream to the storage after satisfying the demand, and again during this period up to t0, water will be taken from the storage to satisfy the demand. In order to find out this capacity, this is the average flow rate. what we do is we draw lines parallel to this and then the difference between these two lines is the required storage. These lines are drawn at the ridge and the valley. So the highest portion and the lowest portion of the mass curve, which is the volume versus time, the difference will be the required storage. So this S is the required storage to satisfy a continuous demand at a constant rate which is equal to the average flow rate. So this is the maximum sustainable demand at that location. And if you look at this figure, it is clear that when the mass curve is flatter, that means we are getting water at a smaller rate, and therefore water has to come from the storage into the stream to satisfy the demand. There are various other options or various other variations in demand. For example, the demand may not be constant, the demand may not be as high as Q average, the demand may be smaller. In that case, our storage requirement will be smaller. For example, if the demand curve, which in this case we have taken parallel to this Q average line, if it is flatter, then we will have to draw a line which is parallel to this demand line, and this will result in a smaller storage for that satisfying that particular demand. Now the demand itself may be varying. So your mass curve may look like this, and the demand itself may look like this. So instead of a continuous constant demand, we say that the demand may be varying with time. If you are looking at a large term, let's say annual time period, let's say this is 1 year, which is what we typically do in water resources project, because the rain, runoff, all these things are cyclic based on an annual cycle. So typically we look at a 1 year period and see sometimes the demand may be very high, maybe in summer months the demand may be high, depending on the locality whether the demand is for irrigation or residential requirements. The demand may be high during summer, it may be low during winter, and so on. So the demand itself may be changing. Water supply, of course, changes. So in that case, what we do is we find out the maximum difference between the demand and the available water, which is the runoff, cumulative runoff volume. So the maximum difference between these two ordinates will give us the required storage capacity. So we will now discuss one more aspect, which is yield related to the mass curve, and typically we will talk about annual flow in the stream. As we have said, looking at short term, week or days is also possible, but generally when we say yield, it would be annual yield of the stream. So if you look at the hydrograph of the stream, typically this time will now be January, February, March, and so on. The hydrograph may look like this, small discharge here, then in monsoon months it will go up, and then again in winter months it may come down. There may be smaller peaks here, valleys in response to individual storms, but in general the hydrograph will look like this, and yield would mean what is the amount of water available in the stream over the period of a year. So this would be cumulative volume typically over the year. So yield is an important concept because it tells us how much water is available to us over the period of the year. Hydrograph will give us what is the maximum flood in the river, so we can use that to design flood control works. We also have this minimum flow here, and as we have discussed earlier, there are three different kinds of streams. We have perennial, and if you draw this hydrograph for perennial, you will see that throughout the year there will be some water available in the stream. And therefore, if you draw the flow duration curve, the 100% will correspond to some finite non-zero value of Q. But if you have an intermittent or ephemeral stream, then the flow duration curve would look like this, where 100% may be here and this may be 70 or 80%. So this means that 20% of the time there will be no flow in the stream. So this is also an important aspect which has to be taken in consideration when we are designing a project, that 20% of the time there will be no flow in the stream. So if we are generating power, there will be no power available during this time. So we will finish here, and in summary, in today's lecture, what we have discussed is how to develop hydrograph for ungauged basins using synthetic unit hydrographs, how to develop mass curves and flow duration curves which help us in analyzing the flow in a river in terms of what is the dependability of various discharges, what is the storage required in order to satisfy some demand, and what is the maximum demand which we can meet based on the given flow pattern.